Question number 2 is oddly prescient, considering what's going on in the world around us right now, but nevertheless is another great opportunity to use one of the options that we discussed in question number 1. Either guess and check combined with graph and calculator, or solving an equation with logs. For the sake of being helpful, I'm going to show in the remaining videos only the solving with logs strategy, because it is kind of weird to watch somebody just guess and check a bunch of things, and that's a skill that many of us who use guess and check already have. If you're a guess and check person by nature, you don't need me to show you how to do that. It's probably because you do it already anyway, and you probably do it more efficiently than I do. So I'm going to show the log methods. If that's not your method of choice, you don't have to watch any of these videos. You can just use the answer keys and your own guess and check strategy to figure out the answers on your own. So again, just use whatever best situation suits you. If you're going to do the log strategy, we're basically going to do everything we did in number 1, even though this question in number 2 doesn't subdivide the parts A, B, and C the way they did in the previous example. I'm just going to take it upon myself to write an equation and solve the equation with logs without doing part A, part B, and part C. So, first thing I did to build an equation was to read the question and look for where the numbers are hiding. Since all of the words in this question look like words, none of them look like numbers, I'm going to have to read really critically, maybe even read between the lines a little bit, to try to pick up on the subtext here. I'll also just give you a hint. Everything in this entire section is going to be geometric or exponential in nature. So all of these problems are going to fit the same template we initially used in number 1. Initial times multiplier to the power of x, which means we're looking for and reading for information about an initial value and information about a multiplier as we read the question. So it helps to kind of go into each question knowing what you're looking for, so that way you're not reading it 4 or 5 times just feeling like you're lost. So we've got this person studying a mysterious virus, taking a sample of cells infected by the virus. Currently there's 1 viral cell in the sample. The word 1 is a number, even though it doesn't look like it. I'm going to circle it. Always circle the numbers if they give you stuff. Each day that he monitors the sample, the number of viral cells in the sample doubles. That's another number in disguise. I'm going to circle that. It says, how many days will I need to monitor the sample for the number of viral cells to exceed 1 million? That is a number. Now I didn't circle it, and I'll explain why in a second. This might give you a good strategy to utilize going forward. The reason I didn't circle this is because that's part of the question. Anything that's part of the question is not really something that I feel confident building into my equation yet. The parts that come from definitive sentences, like 1 viral cell in the sample, period. Number of viral cells in the sample doubles, period. Those are bits of given information. We're sure about those. The question gave us those with certainty, so those are the numbers I want to consider for my equation. The 1 million is going to be part of eventually what I'm going to solve for, but I'll deal with that in a second. So question mark words I usually leave to the end of my thought process, and I start with the numbers that come from definitive statements. Currently there is 1 viral cell, and the number of viral cells is doubling. Remember how we're trying to fit those 2 pieces of information into initial value and multiplier roles? 1 viral cell currently seems to be an initial value. Right now, at the moment we're starting to look at this thing, there is 1 viral cell, and since we are doubling, we know we can translate that in our heads to multiplying by 2, so it seems as though the equation I can build is 1 times 2 to the x. Now I don't necessarily know if I want to write y equals for this, because I know that that's where the question comes in. We want to know when we're going to hit 1 million cells. So that's essentially like saying, hey, when is x, like how much time is it going to take? Remember how in number 1, x was the number of hours? This question is measuring days, but same idea. How long is usually the variable. How long will it take to reach 1 million? That means we need to think about when our equation will be equal to 1 million. That's the equation we're going to solve. Again, you can guess and check if you want to, totally fine, but I'm going to show how to solve this with logs. First thing I'm going to do is just evaluate order of operations here. I need to get rid of the 1 first, then I need to get rid of the 2. Getting rid of the 1 is kind of redundant because you're just dividing by 1, which isn't substantially going to change anything. 2 to the power of x is still going to be equal to 1,000,000. But that might give us some peace of mind because now this looks like those exponential problems, the problems that we saw in previous examples, the problems that we saw on page 11. Is now I can do the same steps that I did on page 11. Introduce a log on both sides. So log of 2 to the x equals log of 1,000,000. And again, if you're like, wait, Herbert, how did you know that this is the time to introduce a log? It's basically because we were stuck with something exponential. And we want to get rid of something exponential. The way to get rid of something exponential, namely to get rid of the thing that is exponentiating the x, that's the thing that's stuck to the x, is to use a log. That's pretty much what we're doing here. We're getting rid of the exponential part algebraically by using a log. Now, when I say use a log, I'll refer specifically to that power property. We're going to bring the x down to the front and call it x times log 2. Remember, that was why we did it way back when we learned this earlier this week. It was to turn this into an algebra problem we can solve. X is multiplying log 2. We can deal with that. We can deal with multiplication. We'll divide to get rid of the log 2. That gets x by itself. That's what we wanted. And now we have this giant fraction, which looks crazy, but no big deal. That's why we have calculators. We can deal with this. Log of 1,000,000, close the parentheses, divided by log of 2 is 19.932, if I round to 3 decimal places like is standard. Sorry, you can't see that. There we go. 19.932. And if I read this back to myself in context, it says, how many days will he need to monitor the sample? 19.932 days. And if you want to check, you have 2 options. Obviously, you can check the answer key if you want to, or you can go back to your original equation. 1 times 2 to the power of that answer. Notice you can use the copy-paste feature if your calculator has it, or you can just type 19.932 or all of the little decimals, and sure enough, you get 1,000,000. If you wanted another option, you could, if you have a graphing calculator, scroll to the 19-ish area in your table, and sure enough, that's where we change from 524,000 to over 1,000,000. That's scientific notation. So we know that the change definitely happened between our day 19 and day 20. And that's definitely what we got. Something between day 19 and day 20. So again, logs can make things really helpful. They can give us a direct way of getting to an answer without having to guess. And better yet, they're starting to look really repetitious. The work for question number 1 looks almost identical to the work for question number 2. And that's the goal. Every one of these problems is going to have work that looks virtually the same. So the more consistency you can make here for yourself, the better. And if now you feel like, hey, wait a minute, I'm seeing a trend, you can stop watching videos at any time and just finish solving the problems without me walking you through. I'll keep walking you through them, but every one of these videos is going to start really getting repetitious. And that's the point. So you can see that every example, even if it has different words, is still going to lead you to the same equation with the same steps, the same setup, and the same execution.